Welcome back, everybody. We're diving into the well today. It's this pretty massive new resource for machine learning in scientific research.
Right.
It's basically a whole bunch of really challenging physics simulations,
Yeah.
and the idea is to use them to push the limits of what AI can do,
hmm
especially when it comes to, understanding the world around us.
Yeah.
But before we jump into all the details,
Right.
let's talk about why the well is such a big deal. What's the big deal with the well?
Well, one of the big things about the well is that it's designed to kind of address a key limitation in the field.
Okay.
A lot of the data sets that we've used to train machine learning models for science are, I guess you could say, too simple.
Too simple, yeah.
They don't really capture all those complexities of the real world, like turbulent flows,
Oh, yeah.
gravitational interactions, or how exotic materials behave.
Oh, okay.
So this is meant to change that by providing a much tougher training ground for these models.
So it's kind of like taking those AI models out of the kiddie pool and just throwing them in the ocean.
Exactly, yeah.
Okay.
And that's important because we need these models to be able to tackle those big real-world problems, like predicting climate change,
Right.
designing brand new materials, or even trying to understand how the universe evolved.
Oh, wow. Yeah.
And these are not easy problems.
Definitely not. Yeah.
So they require really sophisticated AI models.
Right.
Ones that can just handle all that complexity.
Okay. I see the vision here. But before we get too deep into the applications and all that, let's break down what the well actually is. What kind of data are we talking about here?
So the well is a collection of data sets, like a huge 15 terabyte collection of data sets spanning 16 different physical scenarios.
Oh,
They've got everything from fluid dynamics to astrophysics to material science.
oh, wow.
All these simulations are done at a resolution that's both challenging for machine learning, but also very relevant to real scientific research.
So it's not just some random assortment of simulations.
Mm.
This is carefully curated to be actually useful for researchers.
That's right, yeah.
Okay.
And to make things even easier, all that data is provided in a standardized format with a PyTorch-based interface.
Okay.
Which means it's very easy to integrate into existing machine learning workflows.
That's a nice touch. Yeah.
Yeah.
Okay. Enough of this high-level stuff. I'm dying to know what juicy simulations are actually in the well. Can we, take a peek under the hood?
Absolutely. Let's dive in.
Okay.
Let's start with fluid dynamics. They've got this one simulation on acoustic scattering, which is basically how sound waves propagate through materials with different densities.
Okay.
And they've included this really cool simulation where the sound waves actually have to navigate a maze-like structure.
Wow. In a maze.
Yeah.
That sounds like more like an art installation than, a scientific simulation. What's the
Yeah.
point of that?
Well, it turns out that even something like that, seemingly simple acoustic phenomena can be super challenging for machine learning models to predict.
Okay.
Because you have those sharp changes in density,
Right.
you get these complex wave patterns,
Oh, okay.
and those are really difficult to capture.
Yeah, that makes sense.
Especially when you factor in that maze-like geometry,
Yeah.
and that has, implications for things like geophysics
Right.
or even medical imaging, where you're trying to understand how waves travel through, these complex materials
Okay.
that aren't homogeneous.
Makes sense. What other kinds of fluid dynamic simulations are in the well?
So they also have simulations of what's called active matter,
Active matter.
which are systems where particles are constantly moving and interacting,
Oh, cool.
kind of like a microscopic dance floor,
Oh, yeah.
where these dancers are constantly bumping into each other and creating these really complex swirling patterns.
Wow, yeah.
And those simulations are particularly challenging because of the long-range interactions between those particles.
Okay.
You can't just look at one particle by itself.
Right.
You have to consider how it's being influenced by everything else around it.
It's like trying to predict the movement of a flock of birds or something, right?
Exactly.
It's not just about the individual birds. It's about how they're moving as a group.
Yeah, it's like collective behavior.
Yeah.
And then the well also includes simulations of shear flow,
Oh,
which is what happens when layers of fluid move at different speeds.
Oh, okay.
Think of a river flowing past a stationary rock,
Oh, right, yeah.
And those simulations are important for understanding a wide range of phenomena, from airflow over an airplane wing to how blood flows through our arteries.
All right, so we've got sound waves in mazes,
Yeah.
microscopic dance floors,
Right.
and turbulent rivers.
Yeah.
What's next on our tour of the well?
Let's journey into the realm of astrophysics.
Oh, what?
So the well actually contains some truly mind-blowing simulations,
Oh, really?
like those of convective envelopes of red supergent stars.
Huh.
These are massive stars in the later stages of their lives.
Right.
And the simulations actually capture the incredibly turbulent flows of plasma within their outer layers.
Red supergiants, those are the ones that will eventually go supernova, right?
Yeah.
Are we simulating a supernova in the well?
Not quite a supernova, but we are simulating the processes that lead up to it.
Oh,
Those spectacular explosions.
right.
Those simulations are important because they give us insights into how energy is transported within these stars and how their structure and stability evolve over time.
Right. That's
What's
fair.
really cool is that these particular simulations are actually cuts from a larger ongoing simulation of a red supergence evolution.
Oh, wow.
So we're basically seeing a glimpse into a specific moment in the life of a star.
It's like a single frame from a cosmic movie or something.
Exactly.
Okay, red supergiants are pretty impressive, but what about those cataclysmic neutron star collisions?
Right.
Everyone's talking about those. Did the well manage to simulate one of those?
They did, actually.
Oh, wow.
They have simulations of post-neutron star merger disks, which is basically the swirling infernos of matter and radiation that form after those two neutron stars collide.
Okay.
Those collisions are some of the most violent events in the universe,
Yeah.
and they're actually responsible for creating many of the heavy elements that make up our world.
Wait, so the gold in my ring was forged in a neutron star collision?
It very well could have been, yeah.
That's incredible.
It is, and those simulations are actually helping us to understand those incredibly complex processes
Okay.
that are involved in creating these elements.
Right.
And they're also pushing the boundaries of what we can actually simulate because they require such sophisticated numerical techniques
Right.
to capture that interplay of gravity, magnetic fields, and nuclear reactions
Oh, wow.
all happening at the same time.
So we've gone from like the heart of a dying star
Right.
to the chaotic aftermath of a neutron star collision.
Yeah.
What other cosmic wonders are hiding in the well?
Well, how about the interstellar medium?
Oh,
That vast expanse of space between the stars.
right. Yeah.
It might seem like empty space, but it's actually filled with gas, dust, radiation, and that's where new stars are born.
So it's like a cosmic nursery.
Exactly.
That's cool.
And the simulations in the well, explore that complex interplay of turbulence, gravity, and cooling in that interstellar soup,
Right.
giving us insights into the processes that govern star formation.
Okay, so we've explored those turbulent hearts of dying stars,
Yeah.
the fiery aftermath of neutron star collisions,
Yeah.
the vast star-forming regions of the interstellar medium.
Yeah.
What an incredible journey through the world of astrophysics.
Yeah, pretty wild.
But I'm guessing we're not done yet, right?
No, not quite.
We still have one more scientific domain to explore: material science.
We do, yeah.
Okay, so material science.
Yeah.
What's in store for us there?
We've got those strange elastic fluids to look at.
Oh, okay. The ones that exhibit something called viscoelastic instability.
Viscoelastic instability. That sounds like something straight out of a sci-fi movie.
It kind of is.
What makes these fluids so strange?
Well, these fluids are basically dilute polymer solutions, and they have this unique combination of viscous and elastic properties.
Okay.
Imagine like a really thick honey that can also stretch and recoil like a rubber band.
Wow.
And under certain conditions, these fluids can become unstable, exhibiting all sorts of strange and unpredictable behaviors.
So it's like trying to simulate a material that's constantly changing its mind about whether it wants to be a liquid or a solid.
Yeah, that's a pretty good way to put it.
Okay.
And that unpredictable behavior makes it super difficult to model these fluids using traditional methods.
So they had come up with some new creative ways to model these fluids.
Exactly.
Oh, yeah.
And the well includes simulations that actually capture the details of this viscoelastic instability.
Providing a very valuable data set for researchers developing those new machine learning models for material science.
Okay, so we've got
Yeah.
sound waves in mazes,
Right.
microscopic dance floors, turbulent rivers, the turbulent hearts of dying stars,
All right.
the fiery aftermath of neutron star collisions,
Yep.
the vast star-forming regions of the interstellar medium, and now strange fluids exhibiting this unpredictable behavior.
Yeah.
The well is truly a treasure trove of scientific data.
And we've really only just scratched the surface.
Oh, wow.
There are so many other fascinating simulations in the well, each exploring a different aspect of our physical world.
This all sounds really exciting, but why even go through all this trouble to create the well?
Yeah.
What are we hoping to achieve with all this data? What's the goal here?
The well is designed to address several key challenges in the field of scientific machine learning.
Yeah.
One of the biggest challenges is incorporating physical constraints into those machine learning models.
Physical constraints. What do you mean by that?
Well, many physical systems are governed by fundamental laws, right?
Right.
Like the conservation of energy or the second law of thermodynamics.
Right.
But traditional machine learning models don't always respect these laws.
Oh, yeah.
They can make predictions that violate these constraints, which isn't very helpful when you're trying to model those real-world phenomena.
So it's not enough for the model to just make accurate predictions.
Right.
It also has to make predictions that are physically plausible.
Exactly.
Yeah.
And that's a really big challenge for those machine learning researchers.
Right.
Like, how do you design a model that can respect the fundamental laws of physics?
Right.
The well is providing this valuable platform for exploring different methods for incorporating these constraints.
Okay, so making sure those models actually obey the laws of physics.
Right.
That's a big one.
Yep.
What other challenges the well designed to address?
Another key challenge is developing models that are stable and robust over long periods.
Right.
Many physical systems, like the climate. Oh, right.
They evolve over these very long timescales.
Yeah.
If you want to use machine learning to make predictions about these systems, you need a model that can maintain its accuracy over those extended periods.
Right.
And that's something a lot of models really struggle with.
That makes sense.
Accuracy in the short term isn't enough. You need a model that can extrapolate accurately into the future.
Right. So long-term thinking, essentially.
Exactly.
Okay, so long-term thinking, obeying the laws of physics. What else? What other challenges?
Another tricky one is developing models that can generalize to unseen parameters.
Unseen parameters.
So many simulations are run with a specific set of physical parameters.
Right.
But in the real world, those parameters can vary widely.
So it's like training a model on Earth's climate and then trying to use it to predict the climate on Mars.
Yeah, exactly like that.
Okay.
You need a model that can adapt to different conditions.
Yeah, makes sense.
And finally, there's the challenge of something called inverse problems.
Inverse problems. Instead of predicting the outcome of a simulation,
Right.
can we actually use the outcome to infer the underlying physical properties?
Oh, okay.
For example, if you observe the light from a distant star, could you use machine learning to actually figure out its temperature and composition?
Well, that's like reverse engineering the universe with machine learning.
Exactly, yeah.
Okay, I'm starting to see the scope of what the well is trying to achieve here.
Yeah.
It's not just a collection of really cool simulations.
Yeah.
It's a call to action for these machine learning researchers to step up their game and tackle some of the most fundamental challenges in science.
Absolutely.
But before we dive into those challenges in more detail, I think it's worth taking a closer look at how these simulations were actually created.
Right.
What kind of tools and techniques went into building the well?
Well, creating such a vast and diverse collection of simulations required a massive collaborative effort, to be honest. The creators of the well actually brought together this whole team of domain experts in fields like, astrophysics,
Right.
fluid dynamics, material science,
Okay.
and of course, those numerical software developers.
So we've got astrophysicists simulating stars,
Right.
fluid dynamicists modeling turbulent flows, material scientists exploring strange fluids.
Yep.
It's a real scientific dream team.
Yeah, definitely.
But what kind of computing power did they need to pull this off? We're talking like 15 terabytes of data here.
Yeah, generating these simulations definitely required some serious computing muscle.
Okay.
The researchers used a variety of high-performance computing clusters,
Okay.
often relying on hundreds of CPU cores to run those simulations.
Wow.
And they also used a range of specialized software tools, and some of those were actually developed specifically for this project.
So they not only created this amazing data set, they also developed new tools to simulate the universe.
Yeah.
That's impressive.
It was a lot of work, but, all of this effort was made to ensure that the well is a valuable resource for the scientific community.
Right?
They really wanted to provide researchers with a set of benchmarks that would push those limits of machine learning and inspire, brand new breakthroughs.
All right, so now that we've explored the motivation behind the well, gotten a little taste of these incredible simulations,
Right.
I'm ready to dive back into those specific challenges that we touched on earlier. Where should we start?
Let's start with one of the most fundamental challenges, incorporating those physical constraints into those machine learning models.
Okay.
How do we make sure those models respect the laws of physics?
That's a great place to start. What are some of the approaches that researchers are exploring to address this challenge?
One really promising approach is using something called physics-informed neural networks.
Physics-informed neural
Yeah.
networks. That sounds intriguing. Tell me more.
Okay, so these are basically neural networks that are designed to incorporate those physical laws right into their structure.
Okay.
It's like baking those laws of physics right into the model itself.
Oh, wow.
So it can't even make predictions that would violate those laws.
So instead of just learning from data,
Right.
these physics-informed neural networks are also learning from, like, our understanding of the universe.
Exactly, yeah.
Wow, that's cool.
So for example, you could design a neural network that's constrained to conserve energy
Right.
or to obey that second law of thermodynamics.
Right.
So that way, even if the data is noisy or incomplete, the model will still make predictions that are physically plausible.
That's really clever.
Yeah.
It's like giving the model a set of guardrails,
Right.
to keep it on track. What are some other ways that researchers are incorporating physical constraints into these models?
Another approach is to use something called symbolic regression.
Symbolic regression. That sounds intense.
It is a little bit, yeah.
What is that?
It's basically a technique that can automatically discover mathematical equations from data.
Oh, wow.
So you can use it to actually find equations that describe the underlying physics of a system.
Okay.
And then you can actually incorporate those equations right into your machine learning model.
So it's like teaching the model the language of physics,
Right, exactly.
so it can understand the rules of the game, so to speak.
Yeah, that's a great way to put it.
Okay, so physics-informed neural networks and symbolic regression.
Uh-huh.
Those are some pretty powerful tools
Yeah.
for tackling the challenge of those physical constraints.
Right.
What about the challenge of stability and robustness over those long periods?
Yeah.
How are researchers addressing that one?
That's a tough one, but there are some promising approaches emerging. One is to use what are called hybrid models that combine machine learning with traditional physics-based models.
Hybrid models. So we're talking
Correct.
about blending the power of AI with the rigor of physics.
Exactly, yeah. Traditional physics-based models are really good at capturing those fundamental laws that govern a system,
Right.
but they can be computationally expensive,
Yeah.
difficult to solve for complex scenarios.
Right.
Machine learning models, on the other hand, they're really good at learning patterns from data, but they can sometimes miss some of those nuances of the underlying physics.
Oh.
So by combining these two approaches, we can hopefully create models that are both accurate and efficient.
It's like having a team of experts working together, right?
Yeah.
Each one bringing their own unique strengths to the table.
Mm.
How do you actually go about building a hybrid model?
There are a couple of different ways to do it. One approach is to use machine learning to learn what we call a surrogate model for a computationally expensive physics-based model.
A surrogate model, so like a stand-in for the real thing.
Precisely.
Yeah.
You train a machine learning model to mimic the behavior of that physics-based model. Then you can use that faster surrogate model to make predictions, which will save you a lot of time and computational power.
That's a clever trick. It's like having a cheat sheet for the physics exam.
Yeah, exactly, like a shortcut.
Okay. What are some other ways to build these hybrid models?
Another approach is to use machine learning to actually improve the accuracy of a physics-based model.
Okay.
So you can use machine learning to learn corrections to that physics-based model or to discover new terms that should be included in the model.
So it's like using machine learning to fine-tune the physics-based model,
Right.
making it even better at predicting the behavior of that system.
Exactly. Yeah.
Okay, cool.
And there's also a lot of excitement around developing new machine learning architectures
Okay.
that are specifically designed for those scientific applications.
Oh, okay.
Traditional neural networks like the ones that are used for image recognition or natural language processing,
Huh.
they may not actually be the best fit for scientific data.
So we need new kinds of neural networks that are like tailor-made for science.
That's the idea. Researchers are actually already developing these new architectures. For example, there are graph neural networks, which are designed to learn patterns from data that's structured as a graph.
Okay.
And then there are those physics-informed neural networks that we talked about earlier.
Right.
Those are also a really promising new type of architecture.
Okay, so we've got those physics-informed neural networks,
Right.
hybrid models, new machine learning architectures.
Yeah.
It sounds like we have a lot of powerful tools at our disposal
Uh-huh.
for tackling these challenges.
You do, yeah.
I'm curious, what are some of the most exciting research directions you see kind of emerging from all of this work?
One of the most exciting directions is the development of machine learning models that can actually discover new scientific knowledge.
Discover new knowledge. So
Yeah.
it's not just about making predictions.
Right.
It's about actually uncovering new insights into how the universe works.
Exactly. Yeah.
Yeah.
Imagine using machine learning to discover like a brand new law of physics
Wow.
or to identify a previously unknown phenomenon.
Okay.
That's the kind of potential we're talking about.
That's pretty mind-blowing. It's like having an AI scientist working alongside us.
That's a great way to put it. Yeah.
Okay.
Another exciting direction is the development of machine learning models that can design and optimize those really complex systems.
Okay.
So, things like new materials with specific properties or even more efficient energy grids.
Okay.
Those are real-world applications that could really have a major impact on our lives.
So we're not just talking about like theoretical advancements here.
No.
We're talking about using these tools to solve like real world problems.
Exactly, yeah. Making a tangible difference. And one area that I'm personally really excited about is the development of machine learning models that can explain their predictions.
Explain their predictions.
Yeah.
Most machine learning models are like black boxes, right?
Mhm.
They can make predictions, but they can't really tell us why they made those predictions. Why is it important for them to be able to explain themselves?
Well, in science, it's not enough to just be right.
Right.
We really want to understand why something is right.
Okay.
We want to know those underlying mechanisms, those cause and effect relationships.
Okay.
If we can develop models that can actually explain their reasoning, it will give us a much deeper understanding of the systems we're actually studying.
It's like having the AI model teach us what it's learned
Right.
so we can gain those new insights.
Exactly, yeah. And the well is a really valuable platform for developing these explainable AI models.
Okay, so we've got models that can discover new knowledge, models that can design and optimize these complex systems,
Yeah.
and models that can explain their predictions.
It's a really exciting time to be in this field.
It sounds like the future of scientific machine learning is incredibly bright.
It really is, and the well is playing a crucial role in making that future a reality.
All right, after that fascinating overview,
Yeah.
let's dive back into the well and look at some of those simulations in more detail.
Okay.
We've already talked about the acoustic scattering simulations,
Right.
but I'm really curious about those active matter simulations.
Okay.
Those, microscopic dancers we talked about earlier.
Yeah, those are fun.
What makes them so unique and challenging from like a machine learning perspective?
Well, one of the things that's so interesting about active matter is that the collective behavior of those constantly moving and interacting particles,
Right.
it's really more than just the sum of their individual actions.
It's that flock of birds.
Right.
Exactly.
Each bird has its own behavior, but the flock as a whole moves in these really complex ways
Right.
that you couldn't predict just by looking at a single bird.
Exactly, yeah.
Mm.
And these emergent patterns, they're incredibly difficult for machine learning models to predict.
Because, again, you can't just focus on one particle in isolation. You have to consider how it's being influenced by all of the other particles in the system.
That sounds like a computational nightmare.
It can be, yeah.
How did the researchers even go about creating these simulations?
They used a method called a pseudospectral method,
Okay.
which involves representing the positions and velocities of those particles as a combination of waves,
Okay.
and then using these mathematical tools to evolve those waves forward in time.
Got it.
This method is very efficient for simulating systems with complex, evolving behavior, but it still requires, significant computing power.
So they're basically simulating these microscopic dancers as a collection of constantly shifting waves.
That's a great way to think about it, yeah.
That's wild. And they were able to capture like not just the movement of the particles, but
Yeah.
also like the interactions between them.
They
That's-
captured those hydrodynamic and steric interactions.
Wow.
They even ran these simulations on powerful GPUs, which still took about 20 minutes per simulation.
Okay, so we've explored those tiny dancers.
Right.
Now I'm ready to zoom back out to those giant red supergents.
Okay.
What makes those simulations so challenging from a machine learning perspective?
One of the key challenges in modeling those red supergents is capturing the dynamics of convection. That incredibly turbulent process
Right.
that actually transports energy from the hot core to the cooler outer layers of the star.
So it's like a giant cosmic boiling pot.
That's a great way to visualize it, yeah.
Okay.
But it's a lot more complex than just boiling water.
Oh, wait, bad.
These simulations have to account for this complex interplay of radiation, gravity, and hydrodynamics.
So not only is that plasma moving around in all sorts of crazy ways, it's also interacting with radiation and being influenced by the star's own gravity.
That's exactly right. Yeah. And these simulations were actually incredibly challenging to create.
Oh, okay.
They took over 1,400 hours to run on a massive supercomputer.
1,400 hours on a supercomputer. That's dedication.
It is, yeah. But the results are incredibly valuable because they give us a much deeper understanding of how these stars evolve over time.
Okay, red supergiants are impressive, but those neutron star collisions,
Right.
those are on a whole other level.
Yeah.
What makes those simulations so difficult? What makes them so hard to model?
Neutron star collisions are some of the most extreme events in the universe.
Yeah.
And simulating them accurately requires a mind-boggling level of complexity.
I can imagine.
Yeah.
You're dealing with incredibly dense objects,
Mhm.
intense gravitational fields,
Right.
temperatures that are just off the charts.
Exactly. And you can't forget about those magnetic fields and the nuclear reactions that are happening.
Right.
The researchers who created these simulations actually had to use a code called New Biz Light,
Okay.
which is specifically designed to handle all the complexities of general relativity.
General relativity again. It seems like every time we talk about the most extreme events in the universe, general relativity comes up.
It's unavoidable when you're dealing with objects as massive and dense as neutron stars.
Right, yeah.
And these simulations are incredibly detailed.
Okay.
They actually capture the formation of that accretion disk around the merged neutron stars,
Right.
the ejection of that hot material,
Okay.
and even the creation of those heavy elements.
It's amazing to think that these simulations are actually helping us understand how the very elements that make up our world were created.
It is, yeah. And these simulations provide a ton of data for training and testing those machine learning models.
Okay, after those incredibly intense events,
Yeah.
I'm ready for something a little calmer. Let's talk about the interstellar medium,
Okay.
those vast clouds of gas and dust where new stars are born.
hmm
What are the key challenges in modeling those regions? What makes them difficult to model?
One of the biggest challenges is capturing that multi-scale nature of the interstellar medium. You have these enormous molecular clouds spanning light years,
Okay.
turbulent flows on the scale of parsecs,
Mhm.
and then you have star formation happening on much smaller scales.
So it's like trying to simulate the entire Earth's atmosphere
Right.
from global weather patterns down to like individual raindrops.
That's a great analogy, yeah.
Wow.
And to capture this incredible range of scales, the researchers had to use some pretty clever numerical techniques,
Okay. Like what?
like adaptive mesh refinement.
Adaptive mesh refinement.
Yeah, it's a mouthful, but it's a really cool technique. It allows you to basically focus your computational resources on the areas of the simulation
Right, yeah.
where the most interesting things are happening.
So it's like having a zoom lens on your simulation,
Exactly.
allowing you to see those details without having to simulate the entire thing at the highest resolution.
Precisely. And these simulations were able to capture that complex interplay of turbulence, gravity, and cooling in the interstellar medium,
Right.
all of which play, a crucial role in star formation.
Okay, so we've explored those vast cosmic nurseries. Now let's zoom back into the microscopic realm and revisit those strange fluids that exhibit that viscoelastic instability.
Right, yeah.
What makes those simulations so challenging?
These fluids are kind of a headache to model
Okay.
because they have that unique combination of viscous and elastic properties. They
Wow.
can flow like a liquid, but they can also stretch and recoil like a solid.
So it's like trying to simulate a material that's constantly changing its mind about whether it wants to be a liquid or a solid.
Yeah, exactly. And that unpredictable behavior makes it really hard to simulate these fluids using those traditional methods.
So how did the researchers tackle this challenge?
They used a method called a spectral method,
Okay.
which involves representing the fluid's properties as a sum of waves.
Okay.
And they also used the Dataset software that we mentioned earlier.
Right.
Seems to be a real workhorse for those fluid dynamic simulations.
It does, yeah.
Yeah.
So they're simulating those strange fluids as a collection of like interacting waves.
Exactly. And they were able to capture those swirling vortices that we see in so many fluid systems,
Right.
as well as that complex interplay between the fluid's viscous and elastic properties.
Okay, so we've taken this kind of whirlwind tour through the world of the well,
Yeah.
exploring simulations of everything from sound waves in mazes to the turbulent hearts of those dying stars.
It's been quite a journey.
It has, yeah. It's an incredible data set
Yeah.
that's already having a major impact
Yeah.
on the field of scientific machine learning.
Right.
But before we wrap up, I'd like to touch on one more kind of important aspect of this project, the role of collaboration.
Yes, collaboration is absolutely key to the success of something like the well.
Okay.
This project brought together experts from all these different scientific disciplines:
Right.
astrophysics, fluid dynamics, material science, and of course, computer science.
Right.
And that interdisciplinary collaboration was really crucial
Okay.
for creating such a diverse and challenging data set.
So it wasn't just a bunch of computer scientists sitting in a room coding up simulations.
No, not at all.
Okay.
The creators of they recognized they needed that input from experts in each of those scientific domains
Okay.
to make sure that those simulations were both realistic and relevant to real-world research.
So they had astrophysicists guiding the development of those red supergent simulations, fluid dynamicists providing expertise on those shear flow simulations,
Right.
and material scientists lending their knowledge to those viscoelastic instability simulations.
Exactly.
So it was like a true team effort
Yeah,
with everyone kind of contributing their unique skills and perspectives.
absolutely, yeah. And this collaborative spirit is one of the things that really makes the well such a special project.
Right.
It's a real testament to the power of that interdisciplinary research
Okay.
and a model for how we can actually use machine learning to advance scientific knowledge
Right.
across all these different fields.
Collaboration is definitely key to unlocking the full potential of scientific machine learning. But let's be realistic. Not every researcher has access to a supercomputer.
Right.
Or a team of experts in every single scientific domain.
Right.
How does the well address that challenge?
That's a great point.
Yeah.
And the creators of the well have taken steps to make this resource as accessible as possible.
Okay, good.
All those simulations are stored in the standardized format
Right.
that can be easily accessed and analyzed using those popular machine learning tools and libraries.
So there's no need to learn a new programming language or wrestle with proprietary file formats.
Exactly. That data is ready to use right out of the box. And to even further lower that barrier to entry, the well includes a suite of benchmarking tools and scripts
Oh?
that researchers can use to evaluate their machine learning models on these challenging data sets.
So it's like a one-stop shop for scientific machine learning research.
Yeah, you could say that.
Oh, that's cool.
The goal is to make it as easy as possible for researchers to get started with the well
Okay.
and to contribute to this, growing community of researchers who are working with this data.
That's fantastic.
Yeah.
It sounds like the well is a valuable resource
Yeah,
for both seasoned machine learning experts and researchers who are just starting out in the field.
definitely. It's for everyone, really.
But I'm curious, what's next for the well? What are the long-term goals for this project? What's the future look like?
Well, the creators of the well, they have really ambitious plans for the future. One goal is to continue to expand the data set, adding new simulations that explore even more diverse and challenging physical phenomena.
Right.
They also plan to develop, new tools and resources to make the well even more accessible
Right.
and even more user-friendly. And they're also actively fostering this community of researchers
Okay.
who are using the well to really push those boundaries of scientific machine learning.
So the well isn't like a static project. It's more of a dynamic and evolving resource
Right.
that will continue to grow and evolve as the field of scientific machine learning advances.
Exactly, yeah. It's a living project. It's constantly being updated and improved. And it's a testament to the power of open science and collaborative research.
Well, I'm incredibly impressed with everything I've learned about the well today. It's a groundbreaking project
It really is.
with the potential to completely revolutionize the way we do science. And I'm really excited to see what the future holds for this project.
Me too. I think we're just scratching the surface of what's possible with the well.
Okay, before we wrap things up, I want to leave our listeners with a final thought-provoking question.
I like where this is going.
Could the well lead to the development of hybrid physics ML models
Right.
that combine the best of both worlds, enabling more accurate and efficient simulations of those complex physical phenomena? Something for everyone to kind of ponder as we continue our journey of exploration and discovery.
That's a good one.
Thanks for joining us for this deep dive into the well. Until next time, keep seeking knowledge and stay curious. That's a really interesting question.
It is.
It seems like the well is setting the stage for some pretty big advancements in scientific machine learning.
Definitely.
But before we get too carried away with the future,
Right.
I want to circle back to something you mentioned earlier, the role of benchmarking in the well.
Okay.
Can you elaborate on that a bit? What makes these simulations good benchmarks for machine learning models?
Yeah, so benchmarking is crucial in machine learning because it allows us to compare different models and algorithms on like a level playing field.
Okay.
It helps us identify which approaches are the most effective for certain types of problems.
Right.
And the well is particularly well suited for benchmarking because of the diversity and complexity of the simulations.
Okay, so how would a researcher use the well for benchmarking? Can you give me an example?
Sure, yeah. Let's say our researcher is developing a new machine learning model for predicting fluid flow.
Oh.
They could train their model on one of the shear flow simulations in the well. And then they could evaluate the model's performance on a different shear flow simulation that it hasn't seen before.
Okay.
This would give them a really good sense of how well their model generalizes to new situations.
So the well provides a way to test not just a model's accuracy,
Right.
but also its ability to kind of handle new and unexpected data.
Exactly.
Okay.
And that's really valuable because in the real world, we rarely encounter situations that perfectly match the data we use to train our models.
Right, of course. Yeah.
So we need models that can adapt
Right.
and generalize.
Yeah, that makes sense.
You know, it's like taking a driving test.
Okay.
You don't just drive around the parking lot. You have to navigate real roads
Right.
with unexpected obstacles and stuff.
Yeah, I like that analogy.
Yeah.
So the well is like the ultimate driving test for scientific machine learning models.
You could say that, yeah.
Okay, so the well is a valuable tool for benchmarking,
Yeah.
and it's designed to tackle some really tough challenges in scientific machine learning.
Right.
But at the end of the day,
Yeah.
what's the big picture here?
Right.
What's the ultimate goal of all this work?
The ultimate goal is to use machine learning to accelerate scientific discovery
Okay.
and to tackle some of the most pressing challenges facing humanity.
Like what?
I mean, we're talking about things like developing new energy sources, combating climate change,
Okay.
curing diseases.
Those are some pretty ambitious goals.
They are ambitious, but I think machine learning has the potential to play a truly transformative role in these areas.
Right.
And the well is a crucial step towards realizing that potential.
Yeah, I'm starting to see a common thread here.
Okay.
It's not just about developing fancy algorithms or crunching numbers.
Right.
It's about using these tools to make a real difference in the world.
That's exactly right.
Yeah.
And that's what makes this work so exciting.
Well, I'm incredibly inspired by everything we've talked about today.
Good.
It's clear that the well is a groundbreaking project
It is, yeah.
with the potential to revolutionize the way we do science.
Mm-hmm.
And I'm really eager to see what breakthroughs emerge from this work in the years to come.
Me too. I think we're at the beginning of a very exciting journey.
And as we conclude our deep dive into I want to leave our listeners with one final thought.
Okay.
As we develop these increasingly powerful AI models, it's really crucial that we use them responsibly and ethically.
Absolutely.
We need to ensure that these models are used to benefit humanity and to create a more sustainable and equitable future.
I completely agree with great power comes great responsibility.
Right.
And it's up to all of us to make sure that AI is used for good.
Well said. Thanks for joining me on this incredible journey into the world of the well.
Oh, of course, it was my pleasure.
It's been a real eye-opener.
It has.
And I encourage all of our listeners to learn more about this project
Yeah.
and to consider how they might contribute to this really exciting field.
It's been a pleasure sharing this deep dive with you.
Yeah, likewise.
And to our listeners, keep exploring, keep learning, and keep pushing the boundaries of what's possible. Until next time, I tape ignore.